previous example, we took a look at how we have two charges, and we said that forces on each other were equal and opposite. And we also considered their masses and talked about the accelerations on them. Let's also take a look at how this force varies with the distance that we go away from a charge. So if we bring charges further away from each other, then what happens to that force? So another example we have here, the variation of force with distance. Two negative charges, call it Q1, has a charge of negative 2Q, and Q2 has a charge of negative Q. So this is implying that one has twice the amount of charge as the other. They're initially 10 centimeters apart, and the smaller negative charge, minus Q, feels a 900 Newton force. The smaller charge is moved to a point which is now 30 centimeters away from the other charge. Calculate the force on the larger negative charge at this final distance. Now, before anything else, consider that it doesn't matter if we're asking for the force on the smaller or the larger charge, because it's just these two charges, and we know that the size of the forces are going to be the same, so it does not matter which charge we ask about. In this case, the forces will be equal and opposite on those two charges. Make an observation about what happened to the distance and consequently what happened to the force. So let's quickly sketch this out. We have this line that connects our charges together very conveniently. We have this larger charge, let's say here, this was a charge called Q1, and a smaller charge here, call it Q2. And we know that Q1 has a value of minus 2 capital Q, and Q2 has a value of minus capital Q. So whatever the values of capital Q are, it doesn't really matter. The most important thing is that one of these charges is twice the size of the other, or if you say it the other way around, the other charge is half the size of the other. Now, we know that the initial distance between these two, let's call it R subscript A. Okay, so in other words, what I'm saying is that this is the distance R in, let's call it situation A. What we're going to do is we're going to transition from situation A, and we're going to take this smaller charge and we're going to slide it out further to a larger distance, and it's going to be called situation B. So there is such a distance, call it from this larger charge all the way out here, call it RB, to some location which is now 30 centimeters away compared to it being previously 10 centimeters away. So the distance has grown by a factor of 3. It's multiplied by 3. So what we also know is that the force in situation A, so F subscript A, equals 900 newtons. And we just don't know what the force in situation B is. Okay. Let's also write out our distances. So RA is 10 and RB is 30 centimeters. Okay. So how do we go about finding the force in situation B between these two negative charges? So what we're going to do is, since we're missing this information about B and we want it, let's start with an equation that could potentially find what this force is. So let's just attempt to find it. So we know that the force between two point charges can be described by Coulomb's law. So we know that the force equals implied absolute value of K, capital Q, lowercase q of R squared, very generally. I'm going to change this around, though, to format it to our situation. So we're going to take this general equation for Coulomb's law, and we're just going to rewrite it in terms of what we're trying to talk about. So the force in situation B equals K, just some constant, doesn't change at all. We're going to call this first charge, let's call that one Q1, and let's call the other charge Q2. Because in our situation, we are going to call Q1 and Q2. Divided by the distance that separates the two in situation B squared. Okay, so whatever that distance is, we need to plug in the distance that is associated with situation B to get the force in situation B. Now, if we just do a quick check of what we have and what we don't have, now we kind of sort of know something about charge 1, and we kind of sort of know something about charge 2. We don't have the numerical values exactly, but we know something about them. So I'll say that I know them. Now, the distance MB we also know as well. Okay. Let's kind of actually say that these are kind of somewhat unknown. So we could attempt to plug everything in, but we're not going to get a number for it because we do not have the exact numbers for all of these. Now what we can do is we can get it as close as we can to being able to plug in the numbers. So what we're going to do is we're going to plug in for what Q1 and Q2 is in terms of this Q. So we have K. Q1 is said to be minus 2Q. We're going to again drop the signs because we're only calculating magnitudes here. So absolute value just gives us 2 capital Q. And Q2 is said to be just Q. Okay. Whatever the values of Q are, that's up in the air. Okay. So now here's what we're going to do. We don't really have too much to work with in here, but we do know some stuff about situation A. So for instance, we know how much force is felt in situation A and the distance that's associated with it. So we know more information about a different situation than the one we're trying to solve for. So what we can do is we can try to write what we have here in terms of the things that are given in the first situation. So meaning, let's say if I do this, I could, for instance, pull this 2, actually, I could leave it there. I could pull the 2 out front, it doesn't really matter. What's going to be more important is that I write the distance in B as something in terms of A. So I could say that we know the distance in B is 3 times the distance in A. So in other words, RB equals 3 times RA, because RA was 10, RB is 30. So given that we know that, we could put that into here and say that the force in situation B is K. We have 2, and let's just condense this to Q squared because that's Q times Q. So 2Q squared divided by, and again, be careful here, we have 3RA, but that whole thing is squared. So if we were to square this out and we pull out some numbers, what we get is K times 2Q squared on top. And we have, well, we got to distribute the square to both of the things in here, so we have 9RA squared. Okay. Now, we have this more in terms of the information in situation A. So what we're going to do is now separately or in parallel, we're going to write out the equation for A, which is what we know a lot of information about. So the force in situation A equals K. And we have the same 2 charges, so Q1 and Q2, over the distance in A squared. We can plug in the Q1 and Q2 in terms of the 2Q and the Q, so we can write K, and that's going to be 2Q, Q, over RA squared. Now, at this point, what we can realize is that if we take a look at this expression here, it looks very, very, very similar to this expression here. The only thing that actually really distinguishes the two expressions, especially if I write this that this is k 2q squared over RA squared. The only real thing that makes these expressions different is this factor of 9 here. Okay, so in other words, the rest of this stuff here, other than the 9, all this stuff here, is basically identical to this. So if it's all identical, and I can just say, well, they're the same thing, other than the 9, I could replace this stuff with just calling it the force in A. So let's replace this with force A. So therefore, the force in B equals, we're going to separate off the factor of 9, but it's in the denominator, so it's 1/9. And all the rest of this stuff in red is the force in A. So force A. That's it. So the force in B is 1/9 the force in A. So in terms of what the values we have, it's 1/9 of 900, which conveniently makes this force B 100 newtons. That's it. Okay, so the observation is that we had increased the distance by a factor of 3. We went from 10 centimeters to 30 centimeters, so we tripled the distance. But that did not weaken the force by a factor of 3. It actually weakened it by a factor of 9. So what happened was that factor of 3 for the distance got squared, and 3 squared becomes 9. So remember that the force will weaken with the square of the distance. So if you go twice as far, then 2 squared is 4. So the force is 4 times as weak. If you go 3 times the distance, then the force is 9 times weaker because it's 3 squared, and so on, and so on, and so on. So this is a longer way of doing this problem, but it helps you to see why this ends up being what it is. Okay. A lot of times they'll give this as like a multiple choice problem, and you're thinking, okay, well, I don't have 15 minutes to throw at this problem. So there are a couple ways you can cut the corners a little bit. Now, I will point out that one alternative way that you could have solved this was if you were missing Q here, you could have gone to here and then solved for Q and then substituted, but it's the same as just taking this whole thing and plugging it in. So you could have solved for Q in situation A and then get the value and plug it into here. That's an option. The shorter way, though, to do this is to use what's called a proportionality. And this is a very, very, very useful technique whenever you have situations or problems where you're comparing two different things to each other or two situations to each other, which is what we have here. So whenever you do a proportionality, okay, what you do is you take the equation that you want to use to examine the problem, which is F equals K. So we have Q1, Q2 over R squared in our problem. Okay. Here's our equation that we're going to be using because we want to know information about the force. So this is what we need to use. Proportionality means to ignore things that stay constant from one situation to the other or from one thing to another, depending on what you're trying to compare. In this case, when we compare our two situations, the following stays constant or does not change. K does not change. We do not write it. Okay? Q1 and Q2 do not change from situation A to situation B. They are going to be the same charges throughout the problem. So we don't write that either. The one thing that does change, though, is the distance between them. In situation A, it's 10 centimeters, and in situation B, it's 30 centimeters, or 3 times the distance. So you only write the thing that does change, and you include the entire term, meaning if it's squared, then you write squared. So we do write that in the denominator, and the only way we can fill in the numerator without changing the value is a 1. You would otherwise write an equal sign, but it's not technically equal. It's only equal when this is the equation. So what we write is this little symbol that looks like a little fish, or an alpha symbol if you know the Greek alphabet. This is a proportionality. So it says that the force is proportional to 1 over the square of the distance, or the inverse square. So when you attempt to use a proportionality, once you've gotten rid of the things that do not change from one to another, situation-wise or thing to thing, you only plug in the factor that things change by. So for instance, I would say that, the distance tripled, so I use 3. That's it. 1/9. That's it. So what this means is, therefore, the force in B is 1/9 the force in A, given that the distance is 3 times the amount. So we quickly arrive at the same conclusion that we did here without doing all the grinding. So this is a very powerful tool for situations where we compare one to another.